Good evening. Today we have the first lecture of President's Lecture Series at the University of Montana for this academic year. And I would like to thank President Dennison for support of this event. And it is my pleasure and privilege to introduce today's speaker, Professor Toru Maekawa of Toyo University. And probably many of you know that Toyo University is a sister university of the University of Montana. Professor Maekawa is a prominent researcher, scientist working in area of Bio-Nano science. He graduated from Tokyo University in 1983. He held faculty positions at various universities, and since 1993 he is with Toyo University. In 2003 he became the director of Bio-Nano Electronics Research Center at Toyo, and under his direction the center was awarded last year a very prestigious 21st Century Center of Excellence grant by Japanese government. Main scientific interests of Professor Maekawa are in the area of self-organization, self-assembly of particles of different nature in micro, macro, and certainly nano systems. He will also give a talk tomorrow at 2 o'clock in the University Center Theater as a part of the Bio-Nano symposium, Toyo Symposium. And today he will speak about Bio-Nano science and technology. Please welcome Professor Maekawa.
Okay, thank you, Leonid, Professor Karachev. My name is Toru Maekawa. I'm from the Bio-Nano Electronics Research Center, Toyo University. First of all, I would like to thank President Dennison for inviting me to Missoula. Actually, this is my second visit to Missoula, and I would also thank the Montana staff for organizing this special event. And I'm going to talk about Bio-Nano fusion research. And this is our center, small center. The number of researchers are only 12. Very small, but cozy. And we've got quite a few graduate students. And as Professor Karachev explained, last year, the year 2003, we were selected as a 21st Century Center of Excellence in the field of interdisciplinary new science. And the title is Harmony between bioscience and nanotechnology. But we haven't done anything in this field. But today I'm going to show you what we are trying to do. I'm from Japan, right? So first of all, let me give you some idea of Japan. This is a flat world map. Unfortunately, the longitude 0 is located at Greenwich, London. So based on this, see, Japan is located here in the Far East, right? And do you know where Montana is? So this is Montana, very far west. See, the time difference is 16 hours between Japan and Montana. So I've just arrived here yesterday. And, you know, this is North America. And let me show you Asia. So we have many big countries in Asia, like Russia, China, India, Kazakhstan, and Saudi, and Israel is part of Asia, Turkey, Iraq, Iran, Pakistan, Bangladesh, and Thailand, and so many countries. But as you see, Japan is isolated. It's surrounded by water. Just like Britain is isolated from continental Europe. So let me focus on Japan and the United States. Japan consists of 4 main islands, plus many, so thousands of islands. And this is Hokkaido, can you see? It's very cold in winter, as cold as Russia. And our largest island is called Honshu. And along the Japan Sea, we have lots of snow in winter. But it's quite hot in summer. And this is the sunny side. It's very mild, except this northern part. And this is Shikoku. This is Kyushu. They're very mild weather-wise. And we also have southern islands, semi-tropical islands, just like Hawaii. So I hope our next symposium will be held in Okinawa or Hawaii. And let me compare Japan with the United States. You know, the capital of Japan is Tokyo. Many people believe that Beijing, but it's not true. Tokyo. And the area, America is huge, so more than 20 times bigger than Japan. Right? So from a geographic point of view, so America is much superior to Japan. But I found one thing which Japan is better. The coastline. As we are made of many islands, so coastline is bigger. But if you see the fractal structure of coastline, in fact, this is much longer. So you can enjoy a nice beach in Japan. And the population of America is more than double compared to Japan's population. This is Montana. So let me compare Japan with Montana. Seems huge for us. And capital, you know, Helena, right? Actually, this one state is bigger than Japan. It's incredible. So it's huge. If you see the population, just 900,000. So, in other words, Japan is very condensed, right? So, so I'm very happy to be here in this spacious state. So, of course, you know, this is Missoula. I'm from, so our center is located in Kanto area. This is. Let me show you Japan from space. The greenery part represents forest or mountain. So, in fact, the 70%, more than 70% of the land is mountainous. So, and fortunately, the green part is still growing, quite unusual. And there's yellow parts of flat land. So people are living in those places. This is Kanto Plain. You know, the capital of Japan, Tokyo. Tokyo is located here. Let me show you Tokyo 400 years ago. It used to be called Edo, right? So people used to travel on foot. And the shogun Tokugawa built several roads for travelers. So the most famous one is Tokaido, from Edo to Kyoto, the former capital. This is the starting point of the journey, Japan Bridge. It's still in Tokyo. This is, the Japanese symbol, Mount Fuji. It's beautiful because of the caldera straight from the sea level. But Tokyo now. So this is a city hall. A bit silly using lots of tax. See, they have a city hall. This is Shinjuku skyscrapers. It's just like Los Angeles or New York. And let me show you bullet trains. So now we have Shinkansen. After the privatization of railway, we have now 6 companies. They are developing different types of bullet trains for different purposes. But the first one is the speed is more than 350 kilometers per hour. Right? Then if you go to different places, so you see a different bullet trains. So now, bullet train and Mount Fuji. Actually, Mount Fuji hasn't changed for 100 years. So it's still beautiful. So this is Tokyo, and our center is located in Kawagoe, quite near Tokyo. But it's very old-fashioned in contrast with Tokyo, very old. It's located 30 kilometers from central Tokyo. Let me compare Kawagoe city with Mizura. It's slightly bigger. The population is slightly bigger. This is Kawagoe now. It's called Koedo. Ko means small or little. Edo means Tokyo. So Shogun used to visit Kawagoe, and he liked it. So it's called Koedo. So we still have old-fashioned houses. You can see the big head. So actually, these heavy roofs are better than light ones in the case of earthquake. So they survived during the big Kanto earthquake. And we have Kitain Temple. So we have many, many temples and shrines. This is the bell tower. They are still using this 4 times a day. They also used to use this bell tower as the watchtower for fire. Then we have Kawagoe Festival. That's crazy, you see, like a Rio Carnival. And in Japan, there are many, many festivals, and they are quite unique. So in winter, you can see Mount Fuji from Kawagoe. It's very clear, 200 miles from Kawagoe, but still you can see the clear shape. By the way, we hardly have snow. Our campus is located in Kawagoe, and this is a railway. This is a nearby station called Tsurugashima. So it takes about 40 minutes from central Tokyo. And you walk to the campus. We have a forest here, and the first building you see is the administration office located here. Actually, it won the unusual design prize in Kawagoe. And we have Pentagon Library, which is surrounded by a Pentagon lecture room buildings. And our center is located here, so small center. So what we are doing there is nanotechnology. But probably you know many things about nanotechnology. It was MIT or IBM, so they're showing their power using lots of money on nanotechnology. One example is trying to write a character, controlling single atoms. But it costs a lot, so we can't afford doing that. So we have no money, in fact. So I'm interested in the self-organization or self-assembly of the nanoparticles or nanomolecules. So we want to know what occurs when we leave them, setting the temperature at a certain value or pressure. See? And we see the actual structure and we think about the application. So we don't set a particular target in advance. We see first and then we see the application. So there's no failure in this research. And we also developing nanoelectronic devices. But again, once again, we don't want to compete with the monsters. The second subject is bioscience. So we focus on, in particular, extremophiles. Extremophiles is a microorganism which can survive even under extreme conditions, such as high temperature, high pressure, or alkaline conditions. So there are creatures which can survive even at water boiling point or in Mariana Trench. There are survivors, lots of survivors. No light, and the pressure is more than 1,100 atmospheric, right? Even so, they're living. And if you take those creatures to the surface, so under 1 atm, they still survive. They don't explode. Imagine 1,100 atmospheric pressure immediately changed to 1 atm, but they can survive for 3 hours or something. So we want to know the mechanism, and we may be able to create a new material, learning from those creatures. And our main subject is Bio-Nano fusion, because nobody has done this, so we want to know what's happening in this field. First of all, we want to know the interactions between nanostructures, inorganic nanostructures, and the biomolecules, cells or microorganisms. Right? So once again, we never fail in this research. We just observe what's going on there. Right? And then we think about the application. Eventually, we want to use the mechanism to medical or environmental programs. Let me show you our brief history. Center was established in 1996, and we won the special grant for the high-tech research center organized by the Ministry of Education, Science and Technology. But as you know by now, we're not doing anything high-tech, so I prefer low-tech, nanotech, right? The 1996, we received New Technology Development Fund from the government. In 2000, I started collaboration with Professor Kuroto. He is a Nobel laureate in 1996 for the discovery of C60, fuel-length soccer ball composed of carbon atoms. And he became the visiting professor of our institute. Then in the year 2001, we started a collaboration with University of Montana. And Professors Kalachev and Derek became our colleagues. We started working. In fact, Professor Kalachev visited us in 1996 for 1 year. And we did several things together, and we published a paper. And in the same year, we received the same grant for the High-Tech Research Center, second phase. The government was quite happy about our result. Then we started collaboration with Paris, and Oxford, Cambridge. Many researchers joined us, and then 2003 we were selected as a center of excellence. But we didn't ask them to choose our center as the center of excellence. So, in fact, I've been very cocky to the government, so I didn't need those things. And they said, so we're doing cheap, low-tech, nanotech, but somehow they chose us. So we are very happy. Let me summarize the collaboration. In 2000, we started the collaboration with Sussex, with Professor Kuroto. Those are Japanese institutions. And in 2001, so Professor Kalachev and Derek joined us. 2002, I started with the Université Paris set. And in 2003, we also started collaboration with the Paris 6. 2004, suddenly we started collaboration with many institutions, Oxford, Cambridge, and that's the National Institute for Material Sciences. And we also started the collaboration with the medical school. So we need some operation. This is Toyo Sussex collaboration. He's Dr. Raymond Whitby. He came to our center for 6 months last year. He's a chemist. This is Professor Kalachev, so we also started the collaboration like this. He visited us several times. Last year, he came to our center. This is Professor Kuroto. I usually visit him once or twice a year at Sussex. And she's Jill Watson. So we are also developing a science program for children up to 10 years old. In this case, they are very good. So they want to learn many things. So often Professor Kuroto gives a workshop for those children. He talks about C60 to those children, but somehow it seems like children like it. And probably university students don't like chemistry or physics, but somehow they like it. And this is Nicole Grobert from University of Oxford. Originally, she's from Max Planck, Stuttgart. And he is a biologist from University of Sussex, Dick Wilson. This is another Nobel Prize laureate, John Walker. You may know him. He won the Nobel Prize for the analysis of ATP, so molecular motor mechanism. And he visited him last year, and he will join us this year. And these are Paris researchers. You can't see Notre Dame. So here, there's Notre Dame, and they're doing experiments just by River Seine. It's very good environment. And, Professor Karachev and Derek with my students. So my students are very happy with the collaboration with them. And the very important collaboration is party. So you can have proper sushi if you come to our campus. So it's different from Californian sushi, right? Very good. And we also have a very nice nouvelle cuisine, French food, probably better than in France. So please visit us. We have many discussions here, so lots of discussion of future research. And we are also educating undergraduate and graduate students based on our research center. So we have basically the School of Science and Technology on our Kawagoe campus, and the School of Life Science on a different campus called Itakura campus. So those students come to our research center, and we're educating them. No, we're not educating, we're doing research together. We're enjoying research together. As I said, so we have only 12 researchers. They're basically professors or associate professors, so they're teaching even to undergraduate students. For the last 7 years, we created 40 doctors, so we're quite happy about that, and the students are motivated. So let me move on to the nano or bio-nano. So what is nano? So to explain this, so we need to know the unit system. You know, the international system of units. In science society, we have to use the international system of unit. So it should be abbreviated to IS unit. But you may know, in English, even in English, it's called SI unit. SI units. Why? Because the unit center is France. Not in America, not in Britain. So it's located in France. So in French, it's called le Système International d'Unité. So it's abbreviated to SI unit. Even in English, you say SI unit. So it's funny. So in SI unit, length is measured in meters, not miles, not foot, not inches, right? So mass is measured in kilogram, not ounce. I can't understand ounce. So 8-ounce steak may be too big for me, but should be mentioned by kilos for me. And time is measured in second. See? So nano is a prefix. So you know milli. Milli is a prefix for 1/1000. So there are 3 zeros in the denominator. So in math, we say 10 to the minus third or 10 to the minus 3. Right? So micro is 1/1 million. So every 3 zeros, we have a special name. So 10 to the minus 6 is called micro. So micrometer, micro machine, you know, so we're talking about, so 10 to the minus 6 meters. This is nano. That's 10 to the minus 9th. Do you know pico? 10 to the minus 12th. Femto is 10 to the minus 15th. See? So we use these prefixes. So let me explain a nanothermal statistical world. So materials are composed of molecules, and molecules are composed of atoms. So the typical length scale of atoms is 0.1 nanometer. Right? It's often called 1 angstrom, but now in SI units, so we don't use angstrom. So we say 0.1 nanometers. And the molecules are in fact moving, right? Oscillating, rotating. So the typical period of the rotation or vibration is a femtosecond. Do you remember femto means 10 to the minus 15 second? That's a typical time scale of these atoms and molecules. In our macroscopic world, the length scale is meters, inches, miles. The time scale is second, or minute, or hours, or days, or year. You can see the gap, huge gap. So what we are seeing or feeling is the statistical average of the molecular motions. So we need statistical analysis. So you learn statistical mechanics, right? So at school you study statistics anyway. The good example is the average value of the molecular kinetic energy is called temperature, right? So when temperature is high, molecules are moving fast. So actually the molecular speed is faster than bullet trains. So in your body, your molecules are moving very fast. So in your arms. So when you measure temperature with the ordinary thermometer, as temperature increases, the molecular motion gets more violent. So we say the liquid is expanding. So when temperature is high, the liquid goes up. Right? So the thermometer means the indirect measurement of molecular kinetic energy. So we use temperature in a macroscopic world. Probably it doesn't mean anything in atomic scale, but we still use temperature. Another example is pressure. So molecules are attacking your body, right? And we don't feel any molecular attack. Otherwise, it may be very noisy. Your ear will be attacked by many molecules. As I said, in 1 second, the 10 to the 15, so molecules hit you 10 to the 15 times, plus 10 to the 23 molecules hitting you. So we average the molecular attack. Then we say the pressure. So we use pressure. So as the number of molecules is very large, the average value is clearly defined, like temperature or pressure. But in nano world, what's going to happen? You see, the atomic scale is 0.1 nanometer. So in 1 nanometer, so 10 atoms in line. Can you make the precise average value? So my height and Kalachev's height can be averaged, right? But it doesn't mean anything in physics or in chemistry. And as a result, deviation is tremendous. So if you try to make an average of those nanoscale properties, sometimes you get negative pressure, negative compressibility. But it means we shouldn't try to average the molecular motion in nano systems. So that's very different from our macroscopic world. You never see your molecules moving outside sometimes. See? You can clearly define the interface in the macroscopic world. So let me explain the nano-statistical typical features. So bracket A is the mean value of a physical property A, let's say A. Sigma A is the deviation, standard deviation. So the ratio of the standard deviation to average value is in proportion to 1 over square root of n. N is the sampling number, in this case, number of molecules, right? So you learn this in statistics. So molecules have no individual characters, so they just follow the statistics. So when n is 10 to the 22nd or 23rd, deviation is ignored, so we don't need to think about the deviation. But we still need deviation to explain the phase transition. So some molecules should be deviated from the mean value, otherwise there's no phase transition. But usually it's ignored. But what's going to happen when n is very small? So deviation becomes significant. That's a very important factor in nano or micro systems. Here, T is the molecular diffusion time. So molecular diffusion time is in proportion to the square of the diffusion length, right? So when L is very small, nano or micrometers, the diffusion time is reduced tremendously. So by reducing the, so by making a microchip, you may be able to encourage chemical reactions. Because for the chemical reactions, two molecules must collide with each other. So the diffusion time is very important. So in nano or micro systems, reaction or biochemical reactions should be encouraged. So we're trying to reduce the size for the disease detection. But it becomes very difficult to disturb the system when it's very small. So we must encourage the chaos. So many people are thinking about the new methodology to disturb the system in nano micro systems for the quick reaction. So here, S represents the surface, V is the volume. So S is in proportion to the square of length, L. The volume is in proportion to the cube of length. So the ratio is in proportion to 1 over L. So when L is macroscopic, surface effect can be ignored. So good example is fluid mechanics equation. So flow pattern is the same even when the water is located on glass or water is located on the silicon or the air located on the anything. So the equation is the same. Surface effect is ignored. So we just name the surface speed is 0. So whatever materials you use. But in nano and micro scales, surface becomes very important. And the so-called similarity doesn't work anymore. So good example is the flow in the water on top of silicon is different from that on quartz. Right? It becomes very important. So, and again, so we are focusing on the cheap, low-tech, nanotech. This is a good example of self-assembly induced by nanoparticles. Those are fellow nanoparticles. So many different patterns are formed automatically. You don't need to make any effort. But there are some universalities. For example, in this case, the particles' locations are always the same. And if you do the same experiment again, you can see different patterns. Right? Every time, patterns are different. But we want to make use of this fact for the nanotechnology. For example, as I said, we can use this wall. So the configuration is always the same. This is being done by Kroto's group, nanoflowers. I think it's beautiful. So that's why we're doing beautiful. So as I said, we haven't got any particular target. So we want to make something unusual or beautiful. Then we ask our students to think about the application. So we never fail in the research. Okay? So anyway, so we want to do something beautiful or unusual. This is a carpet of nanotubes. See? This is done by Nicole Grobert. She can make nanotube sheets. Actually, nanotube electric conductivity and thermal conductivity are very good. So approximately 10 times better than those of copper. Then, this is macaroni, close-up pictures. And then she can put foreign atoms in the nanotube. In this case, iron atoms are contained in the nanotubes. And they're also trying to understand the size effect of superconductivity by coating the surface of nanotubes with the superconductive materials. This is what we are doing now with the WIT-B. These are nanotubes produced by arc discharge. Every time you get different structures. But as I said, we try to understand the electric and the magnetic properties of this junction. Then we use this junction. And sometimes you get 5 fingers from one tube. So we use that for different purposes. This was done by Dr. Hanaji, one of the participants from Toyo. And this is the conventional transistor. Look at this. This is the single-wall nanotubes. I just wanted to show you the size differences. we may be able to reduce the size of future transistors. They are trying to understand the single electron phenomena. This is electron. We put a barrier here, and we apply electric field here. And electron is attracted by the cathode here, but because of the barrier, it can't go through. But under a certain strength of electric field, it can go through the barrier without breaking the barrier. This is a typical nano phenomenon. So in a sense, the deviation is huge, so it can go through. So my student is now playing by applying a magnetic field. So under a certain strength of magnetic field, it can go through. So we may be able to create a magnetic diode or something like that. Anyway, so Dr. Hanaji is trying to make a single electron tunneling device. And we're also trying to produce different structures from furulence or nanotubes. But fortunately, so by accident, we produce those carbon spheres from carbon dioxide at room temperature, 30.12 degrees Celsius. But I can't tell you the mechanism. So we just submitted this paper to Nature, so till then, I can't tell you the mechanism. This is a funny creature, extremophile. It can survive in toluene solvent. Toluene is a toxic solvent. So in hospital, your nurses clean your skin before the injection to kill the germs, but it can survive in a toluene, but it can't survive in water. And so Professor Inoue submitted the result to Nature, but immediately they rejected this. They said it's impossible. But, so Professor Horikoshi called the editors by sending them air tickets to Britain, and they came to Japan and they accepted this article. So never give up. So I'm not a specialist of nerve cells, but Professor Shimizu is trying to understand or trying to control the growth of nerve cells. But somehow, if you put nanotube, which is modified with amino base, they grow towards the nanotubes. So we can control the nanotube configuration geometry now. So probably we can control the growth of nerve cells. And this is a cancer cell. Somehow they capture loads of nanoparticles. Those more than 200 fellow nanoparticles. This has been done by those French researchers. So they are trying to understand the good match, right? The type of cells and the type of particles or the size of particles. This is single molecular motor done by Wilson, and actually Professor Walker won the Nobel Prize for this analysis, ATP actin myosin system. These nanotubes produced by peptide. So Wolfson is trying to produce nanotubes. So the second structure of peptide structures. Right? You can see a Y junction or T junction, and he's trying to coat the surface with gold, and then he's making nanowires. And we want to know the interaction between the peptide nanotube and the carbon nanotube now. And we are also trying to link the nanotubes with the peptide bonding. Let me show you one potential application. So, as I said, by reducing the size of the channels, we can encourage the biochemical reactions. So, actual microchip is like this, tiny. So, we make narrow channels here. This is a close-up channels. You just put 1 picoliter sample, blood sample from your ear, and we try to drive a flow, and we do several different chemical reactions to detect diseases or your health conditions. So, as I said, surface effect becomes very significant in nano-micro system. So, in general, at the interface between the solid wall and the liquid water, you have electric double layer. In a microscopic system, it has no significant effect, but in nanosystems, by applying electric field in this direction, you can induce the flow. It's called electro-osmotic flow. So actually, you can induce flow, and also by electrophoresis, you can separate samples depending on the charges. So let's say this is sodium, and if you can measure the concentration of sodium, so we may be able to detect your health conditions. So this is the demonstration, a good experiment done by Dr. Ichiki. So 2 chemicals are mixed in the microchannel, the 15 microns. 2 chemicals are separated. That's a real-time experiment. So we can separate samples like this. Also, we can induce flow. And now students are playing with the simulation. So some blood sample can be navigated here for the chemical reaction. By changing the polarity, the flow pattern is changed. So in the microchannels, we are trying to control the flow and the sample separation. So this was also done by Dr. Ichiki. We want to sort the blood samples. We don't need those samples. So if you apply AC electric field here, electric force applied here. Oh, we need this one. We don't need this one. Like this, we can choose what we want on a micro scale. So this kind of machine is very expensive and huge, but you can do it using your microscope. And we are also making use of the antibody-antigen reactions to detect diseases. As I said, by reducing the size, we can encourage the antigen-antibody reactions. But it's not enough, so we coat the nanoparticle with the antibody to encourage the reactions. And by changing the type of antibody, you can detect different diseases. Right? In the cell, to encourage the reaction, we're making nano or micro motors. We're using a rotational magnetic field, just 200 Gauss, very weak one. And then it's 0.5 hertz, so you can do it by yourself. Very cheap nanotechnology. And then by changing the frequency, so you can control the reaction speed. Okay, so we've got now a prototype, so mobile cell phone type heart attack detector. But it takes about 5 minutes at the moment. It's not short enough, so it's not quick enough. So our target is less than 1 minute. So in that case, you can detect heart attack in the ambulance, and by the time the ambulance reaches the hospital, the doctor should be ready for operation. That's our dream. So also we're trying to manipulate micro or nanoparticles. Recently, my student invented this method, nanorobot manipulation. Easy, again, 160 Gauss, very low magnetic field. You can change the direction by changing the rotational directions. You also can manipulate big ones. By the way, so the proteins can be attached to the nano or microparticles, so you can manipulate, in a sense, drugs or molecules. This bulky cluster can be moved. Once again, my students are playing. And actually, these are nano or micro ferromagnetic particles, but non-magnetic particles can be manipulated. These are polystyrene particles. They're in the magnetic solver. So, in a sense, magnetic holes are created in these non-magnetic particles. So, we also can manipulate those. Eventually, I hope we can deliver these molecules to your target cell, and the cell capture the particles. So, anyway, so we're trying to do something new. So this is an advert to my students. Probably much easier than you think. And any result is a good result. See? We never fail in research. But we need to be imaginative, right, and creative. And the more important thing is be brave. So we must submit the paper. We must show our result. It's scary if it's first. So let's enjoy the fusion of different nationalities, cultures, and fields, especially because we have no fields barrier. So at least once a year, we hold an international symposium. So last year, we organized this symposium. This is Kroto, Wu-Song, and Professor Kalachev and Derek. So we had a very good time. Yes. And my students are very happy with those top researchers. And they're very good. They give a comment to each student. Very good. So my students are very motivated. And this year, tomorrow, so Montana organized a special symposium on this campus. So please come. And we also have a second international symposium on the 14th and 15th November in Tokyo. See, two Nobel laureates will give a talk. Professor Karachev will also give a talk. So if you have time and money, please visit us. And as I said, we are also organizing a special teaching program to young children. So Professor Kuroto has given loads of workshops all over the world. And when he gives this in Japan, so we do it together. And he's done this for our Kawagoe children. Last year, this was done at the Manchester United Stadium. So those top players helped him. And he also did that in Santa Barbara, in Mexico, and in Germany. So we want to encourage young children to get interested in science. So I would like to thank our colleagues, Professor Kuroto, Whitby, Wilson, Grobert, Bakri, Professor Yoshida. He's also giving a talk tomorrow in Owe, Shimizu, Hanajiri, Ichiki. And I also want to thank my postdoc researchers and students for their hard work. And finally, I want to thank Professor Denison, Professor Kier, Professor Kalachev, Derek, and Montana staff for organizing this lecture. Thank you very much. And thank you for your kind attention. And I hope to see you again. And I want to give you a new result next time. Thank you for your attention.
Thank you very much. We have some time for questions. Yeah, could you please use microphone?
I saw a photograph of a silicon chip and a nerve cell, and they were fused, and they said they actually were growing.
Yeah, could you?
Have they done that?
No, we haven't done that. So we are trying to modify the surface of a carbon nanotube with carboxyl or amino base or several different things. It seems like nerve cells like amino base. And as I showed you, we can manipulate carbon nanotube, especially when you fill the nanotube with iron or cobalt, nickel. So you can manipulate and you can control the structure. Then I hope we can control the growth mode of nerve cells, but I don't know. But we've got patent already.
You do have a patent for that.
No, my
Patents for that?
yes, just an idea, but we're doing experiments. Yeah.
Other questions?
I wonder, the paper that you just submitted to Nature is taking the carbon out of the carbon dioxide at room temperature. Is this something with an industrial application that you could say attach to a smokestack and scrubber?
First of all, I'm sorry, I can't give you the details of the mechanism, but yes, we're trying to use the mechanism for the industry. And we applied for one big fund. Probably we can get it. But I'm just interested in the creation of nanostructures. So we will employ different researchers, including civil engineers and social scientists. Anyway, I hope we can solve the CO2 problems in the near future.
I wonder, just a follow-up, maybe you could outline how does this process work in general, getting from sort of basic research to civil engineering and social scientists, and what role they play? I'm curious about not just that application, but
Yes. First of all, I go anywhere to advertise those things, and there are some odd researchers even at architecture department. So when they show their interest, so I approach them, and then we do something together.
Does this answer your question?
Yes, thank you.
Yeah. Go ahead.
Not a lot has been done on toxicity of nanoparticles and carbon nanotubes. And there's potentially a growing environmental resistance to them. Can you say a little bit about how you approach risk and what kinds of studies have been done in Japan?
Risk of nanoparticles.
But it's up to you. If you want to use that for dangerous purposes, it could be very dangerous. But I think we want to make use of the basic mechanism for environmental or medical issues. Anything could be dangerous.
A question over here. The device that you showed for detection of myocardial infarction, curious, since there's a lot of biomedical applications for this type of technology, just what were you measuring with that device?
Is it a device about blood analysis? Which device? The blood analysis device? Microchip?
You showed a device that measured, that detected myocardial infarction.
Yeah, so we're using the antibody-antigen reactions. Is that right?
Right.
Yeah, so to encourage the reactions, so it's got to be very narrow. Plus, as I said, we have to disturb the system. To disturb the system, we are trying to attach the antibody on the nanoparticles, ferronanoparticles, and as I showed you, we're trying to rotate them to encourage the reaction more and more. And even so, at the moment, it takes 5 minutes or something, so it's not quick enough.
So basically to speed up the reaction time.
Yeah.
I was curious, what was the scale of those particles that you showed in the rotating magnetic field, and also how did you stack? It looked like you had 5 little spherical elements stacked together. How was that?
Yes. First of all, that was for the demonstration, so we used 10 micron in diameter. But we also can manipulate 10 nanometer particles as well. And we use ferro or paramagnetic particles, right? So by applying a magnetic field, dipoles are in line. So attractive force acts on the particles. So you can make clusters, chains. And then by rotating the magnetic field, dipoles rotate like this. Then this particle should move to this. It seems like rotating together, but it's not true. So it's moving depending on the directions of the dipoles. Then you also need magnetic substrate to attract those clusters. So quite easy, the simple mechanism.
They do not stuck together, they move with respect to each other.
Yes, so yes. But it looks like they're moving together.
So you just created random aggregates and then you isolated one of those
Yes.
for that movie that you showed.
Yes, so we applied at first DC magnetic field to attract those. And then by changing the intensity, you can create 2 particle clusters or 3 particle clusters, 4 or 5. As I showed you, it's bulky clusters as you like. So by chance or by accident, you can make many different clusters. And then you navigate whatever you want to the test section. Then we try to rotate a magnetic field.
Other questions? Thank you very much. Thank you, Professor Maekawa.
Thank you very much.
Very enjoyable. Thanks a lot. Oh, that's good. So I made 2 pictures of you.
Oh, thank you.